Thank you, Benno. And well, thanks to the organizers for giving me the opportunity to speak about this, this recent work, which is joint work with Steve Awodey, but actually it benefited from inputs and discussions with several other people, including Mathieu Enel, Reid Barton, Jonas Frey, and Pino Rosolini. So you've already heard a bit about the effective topos from previous talks, especially Jonas' talk gave some useful background on the effective topos and its subcategories. So we'll give you just a brief overview of why it is interesting as a mathematical object. So two important features of this topos is that, well, it is a topos, first of all, a non-Grothendieck one. In fact, it was the first example of non-Grothendieck topos. And in particular, it's locally Cartesian closed. And moreover, since it is non-Grothendieck, it's, well, I mean, it's not a consequence, but it's evidence for being a not Grothendieck. It contains a small subcategory which is complete, but it's not a poset, which is a consequence that must hold for every complete internal category of a Grothendieck topos. And in this way, we can use this complete subcategory to interpret an impredicative universe from an extensional type theory. Yeah, we have to stick to extensional type theories because we are using the topos structure to interpret all the rest. So in particular, we are using the internal logic of subobjects. And yeah, this is due to Martin Hyland, and who also identified this complete subcategory. And then the further work was also done by joint with Edmund Robinson and Pino Rosolini during the 80s. All right, so this is the setting we would like to lift in order to replace extensional here with intentional. So this is the a very active line of research currently, where we would like to find higher versions of the effective topos that would allow us to interpret an impredicative universe in intentional type theory, even univalent, and more generally to provide examples of elementary higher toposes, which are not very common right now. And I mean, of course, we can build higher versions of the effective topos in various ways. And in fact, the effective topos is not the only one that we can think of as housing a notion of computability. There are realizability toposes in general, so we should expect to have higher versions of realizability toposes as well. But how do we speak of the higher version of the effective topos? So one criterion, one desiderata that we want to have is that this higher version of the effective topos should contain the original effective topos as the subcategory of so-called zero types or H sets from homotopy type theory. So those higher objects that are actually contain no higher information and they're just sets. So two elements are either just equal or not. There is no higher homotopy witnessing their equality, or no higher homotopy between their equalities. All right, and well, of course, there is a very straightforward approach to make something higher, which is taking simplicial or cubical objects in that thing. And this is certainly an option that we should consider. But unfortunately, it doesn't satisfy our desiderata. And the intuition is that basically the effective topos is a quotient completion for quotients of equivalence relations. And taking simplicial objects or cubical objects is in some way a completion under quotients of simplices or cubical objects. And the equivalence relations can be regarded as also being a category as a simplicial object themselves, looking at the nerve. So in a way, we're adding those quotients 2 times. One, when we consider the effective topos, and again, when we take simplicial or cubical objects. So we're gonna, and since both additions are free, they don't coincide one with the other. So we end up having 2 quotients of the same equivalence relations. And this means that we are adding sets instead of preserving those that we already had from before. So this is why, in fact, if you look at, say, simplicial objects or cubical objects in the effective topos, the subcategory of 0 types there will be larger than the original effective topos. So today I'm going to tell you a possible strategy to overcome this problem. And yeah, so the basic idea was Steve's, but yeah, it requires a bit of background to be explained. So you've already heard that the effective topos is the exact completion of the regular category of assemblies. You should also know that the category of assemblies itself is a completion, is the regular completion of the category of partition assemblies. And in turn, you can like compose the 2 completions and obtain the effective topos as the so-called X-lax completion, so the exact completion of a category with finite limits. And the category of finite limits in question is that of partition assemblies. And this was done in a series of work by Carboni and various collaborators. Because of this, since we're adding certain colimits, the effective topos must embed in the category of presheaps over partition assemblies, because that's the completion under all small colimits, so in particular those of equivalence relations. If you want, one way to say this is that the unit embedding factors through, both assemblies, because that's also a quotient, a Colimit completion of partition assemblies, and then through the effective topos, and you get to presheaps. It was also observed that we can characterize these 2 categories somehow directly as subcategories of presheaps. And this is done as follows. So here you have the unit embedding, and you can characterize an assembly, A here, as a presheaf on partition assemblies, such that it is covered by a partition assemblies, and it embeds into a partition assembly. And then an object is in the, or a presheaf on partition assemblies is in the effective topos if it admits an exact presentation by assemblies. So by exact presentation, I mean that X is a quotient of A, of an assembly A, and the kernel pair of this quotient is, again, an assembly. So this is what this diagram is meant to represent. Okay, this is nice, but it's not quite enough for us. So let me refine this slightly. Let's say that an object, a presheaf on partition assemblies, is compact if it's covered by a representable. This is often referred to as super compact, actually, but never mind. Super compact. So if you look at Johnston's book, for example, it's called super compact. But I mean, for the sake of this presentation, let me just say compact. And then using this notion of compactness, we can isolate a further subcategory of presheaves, which is given by the so-called coherent presheaves. These are the compact ones, such that the diagonal is also compact, in the sense that the pullback over any compact object is again compact. And so this is, why do we do this? The idea is that this diagonal represents the equality on the object C. And this fact ensures that the equality itself is compact. So this, one problem with the category of compact objects is that it's not closed under finite limits, for example. And this property ensures precisely that coherent objects instead are closed under finite limits. And now this is interesting for us because it turns out that coherent objects in this presheaf topos coincide with the effective topos. And this is the picture that we're trying to, that we will lift to the groupoid case. So we'll do that in 2 steps. First, I will give you a definition of what a coherent groupoid is inside the presheaf on partition assemblies. And then I will give you a Quillen model structure on this category of internal groupoids that is basically needed to speak of zero types and of homotopes in general. And also, this will allow us to, we don't have yet an explicit model, but this is like one of the fundamental structures that we have to consider in order to being able to interpret univalent universe and, well, intentional type theories in general. And now the point is that we will then consider the subcategory of coherent groupoids and the subcategory of zero types, and the intersection of these two will give us back the effective topos. This is the reformulation of the desiderata that I mentioned before, and this will allow us to define the effective 2 topos as this category of coherent groupoids internal to presheafs on partition assemblies. All right. So let's begin generalizing the notion of compact object. Say that a compact discrete groupoid is just a discrete groupoid on a compact object. That's just a convenient terminology. And then a groupoid is said to be pseudo-compact if it's covered by a compact discrete groupoid. Now, covered doesn't mean that you have a surjective functor, but just that that's where the pseudo comes in. The functor is only supposed to be essentially surjective on objects. So internally, this means that this is the underlying graph of the groupoid, and this is the action on objects of this functor here, which is basically all that there is, since K has no non-identity arrows. And then you want, not that this one is surjective, that will mean that the functor itself is surjective on objects, but you want that this composite is surjective. And this means that this guy here is essentially surjective on objects. Now, of course, if you take a discrete groupoid, then this is pseudo-compact, even only if it is compact as a presheaf. Okay, now that we have the notion of compactness for groupoids, we can define coherent ones. So as before, recall that a coherent object, a coherent presheaf, was a compact one such that the diagonal was also compact. So the pullback along a compact object is again compact. And we replicate the definition, but replacing compact with pseudo-compact, and also taking into account of the higher structure of the groupoid as opposed to just an object. So this means that the first diagonal that we are going to consider will actually correspond to the domain-codomain functor. So we'll have to look at a second diagonal in order to close everything under equality. And this is the reason for having 3 conditions instead of 2 as before. So this guy here is the diagonal that you get by pulling back this delta along itself, basically. And again, in the case of discrete groupoids, this notion of pseudo-coherence reduces to the usual one. I have to say that it's not very convenient to work with this definition or to work with pseudo pullbacks in general, actually. So here is a useful lemma if you want a recognition principle for coherent groupoids. Well, basically, it allows us to reduce to another groupoid that satisfies somehow the same properties, but in a stricter way. And reduce meaning that we obtain a weak equivalence of groupoids between them. So by a weak equivalence, or I will just say equivalence actually, I mean an essentially surjective on objects functor, which is also fully faithful. Yeah, so the stricter groupoid is required to have a composite object of objects. The domain and codomain maps pairing the domain and codomain map is compact in the usual sense of presheaves. So the pullback along a compact object is again compact. And then you also want the second diagonal to be compact. Somehow, if you just require the diagonal to be compact, you're considering equality on the lower object by lifting it to the object of arrows. You are saying that you care about equality only of arrows and not of objects. This is the intuition. And between objects, you only care about isomorphisms between them. This is the intuition behind this this lemma. Okay, so this gives us a useful notion of coherent groupoids. And now we come to the Quillen model structure on this category. Now I will just, so this is about the category of internal groupoids, not coherent ones. There is this result by Joyal and Tierney that gives a Quillen model structure on the internal groupoids of any Grothendieck topos, actually. So here I've stated the theorem in the case of presheaves on partition assemblies, which is a particularly nice case since you can also regard this as a category of groupoid valued presheaves on partition assemblies. Somehow the groupoid commutes with presheaves. And so the cofibrations of this model structure are just the functors that are injective on objects. Object-wise, if you regard this as a presheaf of groupoids. And the weak equivalences are what I called before the equivalences. So the essentially surjective on objects functors that are fully faithful. And then, well, the fibrations are given by right-lifting properties, as usual. And yeah, let me mention that in the case of the category of set, this model structure coincides with the usual folk model structure on groupoids. But in general, they're different because in the folk model structure, you want the weak equivalences to be the strong equivalences. So a pair of functors going in the opposite directions that whose composites are naturally equivalent, naturally isomorphic to identities. But we want this model structure, not the folk one, because this one basically will allow us to give a model of a univalent type theory. And that's because it is the restriction to one types of the Quillen model structure used by Mike Schulman to construct univalent universes in infinity toposes. So this is, as I said, we don't have an explicit description of the model, but this feature makes it very likely that we have one eventually. Okay, but now, as I mentioned, this Quillen model structure is on the category of groupoids, so we have to make sure that it restricts to the category of coherent ones. And this follows from a couple of lemmas. So the first one tells us that coherence of groupoids descends along equivalence of groupoids, which again is weak equivalence, recall. Just essentially surjective on objects. You don't have an actual inverse. And this other lemma allows us to go basically the other way around. So, here. Basically, if you look at the factorization of a map as a cofibration followed by fibration, if you know that this one is a weak equivalence, then you can use the first lemma to show that this one is also a coherent groupoid. Well, if you know that this one is a weak equivalence, then it's actually a strong equivalence, so it means that there is another equivalence going in the opposite direction, and you can, again, conclude that this one is coherent from the fact that this one is coherent. That's how the factorization system restricts to coherent groupoids. Another option to prove this is to show that coherent groupoids are closed under comma objects. They're not closed under finite limits or pullbacks in general. That's because we don't take the diagonal on the object of objects to be compact. We take the diagonal on the object of arrows to be compact. So we don't have strict conical limits in general, but we do have comma objects, for example. And this guy here is defined as a comma object. Okay, so now here comes the result that ensures that this construction gives us or meets our desiderata. So if you start with a coherent groupoid, which is also a zero type and fibrant in the sense of the Quillen model structure, then you can prove that its object of connected components is a coherent presheaves on partition assemblies, and the quotient functor is a strong equivalence of groupoids. And for this, still have some time, right?
Yeah, that's it.
Well, yeah, I'm very close to the end anyway. Let me just briefly go through the argument. So you start with the recognition lemma from before. So you replace G with this other groupoid that is compact, that is coherent in a stricter sense, and that is also weakly equivalent to the original one. And now, since G is supposed to be a fibrant zero type, you can show that its domain-codomain map is monic, like here. And now, since we have a weak equivalence here, this left-hand square is a pullback, and therefore, this domain-codomain map is also monic. But we also know that it's compact, so when we pull it back along this cover, we obtain a compact object that embeds into a compact one. So this one is an assembly by the characterization that I mentioned at the very beginning. So we have an assembly here, a partition assembly here, which is an assembly in particular, and therefore we obtain an exact presentation of these connected components by assemblies. So this means that this pi0c is a coherent presheaf. And now, since it is isomorphic to pi0g, we get the first claim. And then the second one just follows from the fact that the back square here is also a pullback, since this guy is monic. And again, since G is fibrant, this weak equivalence turns out to be a strong equivalence. So in this way, we can conclude what we wanted, that the subcategory of coherent fibrant zero types is equivalent to the effective topos. And in fact, it should be the restriction to one types of the effective infinity topos that is considered by Mathieu Hanel, Steve Awodey, and Reed Barton. Yeah, that's all I wanted to say. Here are the references that appeared in the slides before, and that's it. Thank you.
Are there other questions? I would maybe have some questions. So, about this category of coherent groupoids.
Mm-hmm.
So I also had a paper on univalent polymorphism, where also
right.
sort of construct some sort of path category whose zero types are also the things that, basically the effective topos.
Uh-huh.
But then it was only a path category, so I think you managed to construct a Quillen model structure, right?
Right.
But you also mentioned something like you don't have all limits, finite limits, or do your release have pullbacks of vibrations?
Right, that should be the case.
Okay.
But we haven't checked the details yet.
Okay.
Yeah.
I mean,
it's in a way, it's still work in progress. Like the whole construction is just that somehow we managed to get this feature of having the effective topos embedded.
Sure.
And we expect to obtain like an honest model because of should be the restriction to one type of a Quillen model structure considered by Mike Schulman.
Yeah.
In his model.
Okay.
Yeah, I should mention that there are several approaches actually to construct this kind of toposes. Another one is being considered by a student at Johns Hopkins University, who's looking at groupoids internal to the category of assemblies, which in general, if you just look at that category, as I mentioned before, you shouldn't expect to be able to recover the effective topos as zero types. But he is doing another kind of somehow restriction, where he takes those groupoids of assemblies whose groupoid of objects is a partition assembly. And in that way, somehow he manages to get the effective topos back. Then, Sam Speight has another yet construction just using groupoids, but that's that takes quite a different route.
Who was that?
Sam Speight. Yeah, I'm not sure I pronounced the last name correctly.
Final call for questions? No? Okay, then let's thank the speaker again.